Hello viewers, in today's class we are going to discuss one important problem from definite integrals, right? And here we have to evaluate this integral which is from 0 to infinity, and we have log x over a square plus x square, right? Okay, so here we'll evaluate this integral by method of substitution, right? So let us call this integral as I, right? Okay, now here we'll make the substitution, that is x is equal to a square over u, right? So here we'll introduce a new variable u, and we'll take x is equal to a square over u, right? Now, if we differentiate both sides with respect to u, then we'll get dx over du is equal to a square, and the derivative of 1 over u is minus 1 over u square, right? So now dx is equal to minus a square over u square and du, right? So here we have obtained the value of dx, right? Okay, now what we will do, see here the limits of integration varies from 0 to infinity, right? So when x is equal to 0, then what is the value of u, right? See, from this expression u is equal to a square over x, right? So when x is 0 or x approaches to 0, then obviously u approaches to infinity, right? So u is infinity, right? And when x is here infinity, then u is because here when x tends to infinity, then u approaches to 0, right? So now our new limits of integration are from infinity to 0. So now we can write this integral I as infinity to 0, and here we have log x. So now we'll take x is equal to a square over u. Here we have a square over u, and in the denominator we have a square plus a square over u whole square, and for dx we can now write minus a square over u square, and here we have du, right? Now this expression needs a simplification here, so we can remove this negative sign by interchanging the limits, right? Because we know from the properties of definite integrals that a to b f of x dx is simply equal to negative of b to a f of x dx, right? So when we interchange the limits, we get a negative sign, right? So this negative sign can be removed by interchanging the limits. So we have 0 to infinity. Now we have here a log of a square minus log of u, right? So here we have used the properties of logarithm, that is the log of m over n is the log of m minus log of n, right? And in the denominator we have a square, and here we have a raised to 4, and this is u square, right? And here we have du over u square, and we can take this a square outside the integral, right? Okay, so now we have a square, and we have 0 to infinity, and log a square is 2 log a, and here we have log of u divided by, here we can take u square, we can multiply a square with u square, so we have a square u square plus a raised to 4, and in the denominator we have u square, and here we have du over u square, right? So now these two terms get cancelled, and we are now left with a square, and we have 0 to infinity 2 log a minus a log of u divided by, here we can take a square common, so we have a square, and here we have u square plus a square, right? Now this a square and this a square get cancelled, and now we have I is equal to 0 to infinity, and we have 2 log a minus a log of u divided by u square plus a square, or we can write it as a square plus u square, right? So now we have I is equal to this integral. Now we can write this integral as a sum of two integrals or a difference of two integrals, right? Because here we have the negative sign. So now we can write I is equal to 0 to infinity, and we have 2 log a, and this is a square plus u square, and then we have here we have du, and we have 0 to infinity, and we can write a log of u divided by a square plus u square, and here we have du, right? So now we have written this integral as a difference of two integrals, right? And now we can easily see that this integral is same as this integral, right? Because here the variable is x and here the variable is u, right? And again, from the properties of definite integrals, we know that if we have an integral a to b f of x dx, and if we change the variable to t, say, then we have a to b f of t dt, right? So the value of both the integrals are same, right? So we can now replace this integral by I, right? So we have I is equal to, now here 2 log a, here we have du, right? So we have 2 log a, so we can take it outside, so we have 2 log a being a constant, and here we have 0 to infinity, and we have du over a square plus u square, and here we have I, right? Okay, so now we can take this I to this side, so this is I plus I 2I, and this is equal to 2 log a, and the integral of 1 over a square plus u square is tan inverse, here we have 1 over a, and then we have tan inverse of u over a, right? And the limits of integration are from 0 to infinity, right? So here we have used a standard result from integration, that is integral of 1 over x square plus a square is 1 over a tan inverse x over a, right? So now we can write 2I is equal to 2 log a, and we can take 1 over a outside, so we can have here 2 over a log of a, and tan inverse of u over a, and the limits of integration are from 0 to infinity, right? So now this is here 2 and 2 get cancelled, so we have I is equal to 1 over a log of a, and when we take u is equal to infinity, here we have tan inverse of infinity, right? And when we take a u is equal to 0, we have here tan inverse of 0, right? So now we have I is equal to 1 over a log a, and tan inverse infinity is pi over 2, and tan inverse of 0 is 0, right? Because we know that tan pi by 2 is not defined, so we have tan inverse of infinity is equal to pi over 2, right? So here we can now write pi log a divided by 2a, right? So now the value of this integral I, it is equal to pi log a divided by 2a, right? So this is the required value of this integral, right? So here we can now make some deductions from this result, right? See, here this integral is obviously not defined for a is equal to 0, right? So here a should not be equal to 0, right? And the second thing is that if we take a is equal to 1, then what will happen? If we take a is equal to 1 here, see the integral becomes 0 to infinity, and we have log x over 1 square plus x square, taking a is equal to 1 dx, and this is 0 to infinity log of x divided by 1 plus x square dx, right? And now if we take a is equal to 1 in the result, then we'll get I is equal to pi log 1 divided by 2 times 1, right? And we know that log of 1 is 0, right? So this expression is equal to 0, right? So the value of the integral 0 to infinity log x over 1 plus x square dx should be equal to 0 when a is equal to 1, right? Now let us make one more deduction here, right? So the third one is that if we take a is equal to e, right? E is the exponential number. So this integral becomes 0 to infinity, and we have log of x divided by e square plus x square dx, right? And if we take a is equal to e in this result, then we have pi log e divided by 2e, right? And we know that log of e is 1, right? So here we have pi multiplied by 1 because log e is 1, and divided by 2e, so this is pi over 2 times of e, right? Or we can write it as pi over 2 e raised to minus 1, right? So the value of this integral is equal to pi by 2 times e raised to minus 1, right? So here we have made three deductions. The first one is that this integral is not defined for a is equal to 0, right? So a should not be equal to 0. The second one is that if a is equal to 1, then the value of this integral is 0 because log of 1 is equal to 0, right? And the third deduction is that if a is equal to e, then the value of this integral is pi over 2 times e raised to minus 1, right? So viewers, this is how we can solve this integral. Now let us consider one important application of this integral in deriving another integral, right? Suppose we have to find the value of the integral 0 to infinity log of x divided by a square plus x square whole square, right? See, we have just calculated the value of this integral as pi log a over 2a, right? And now let us apply this integral to calculate the value of this integral 0 to infinity log of x divided by a square plus x square whole square dx, right? So what we will do here, will apply the concept of differentiating an integral under the integral sign, right? So let us apply. So now let us call this integral as I1, right? And we have to find the value of I1 with the help of I, right? So here, let us equate this integral to this expression, right? So it means we know that the value of the integral 0 to infinity log of x over a square plus x square dx is equal to pi log a divided by 2a, right? So we have just derived this result, right? So now what we will do to get the value of this integral, will differentiate both sides by taking a as the variable, right? It means we'll differentiate partially both sides with respect to the variable a, right? So what we will write, we'll write del by del a of the integral 0 to infinity log of x over a square plus x square dx, and here we have del over del a of pi log a divided by 2a, right? So here we are using the concept of differentiating an integral with respect to some variable, right? So here if we take this integral, then the variable is x, but when we differentiate both sides, we'll consider a as the variable and x as the constant, right? So it implies that we are differentiating both sides partially with respect to the variable a. So now we can write 0 to infinity taking this operator inside. So we have log of x and dx, and we have del over del a of 1 over a square plus uh, x square, right? Okay, so we have this expression here, and here pi by 2 is a constant, so we can take it outside, and here we have del over del a of log a over a, right? So now the derivative of 1 over a square plus x square with respect to a is given by, here we'll write 0 to infinity log x dx, and here we have the derivative as minus 2a and a square plus x square whole square, right? So this is the derivative of 1 over a square plus x square, right? And here we have pi over 2, and here the derivative of log a over a with respect to a can be obtained by using the quotient rule, right? So what we will do, here we have the second function, then the derivative of log a, that is 1 over a, then we have log a, and derivative of a is 1, and then we have the square of a, right? So now we can simplify this expression. So we have here, we can take minus 2a outside. So we have minus 2a, and then we have 0 to infinity, and we have log x dx divided by a square plus x square uh, whole square, and here we have pi over 2, and here a and a get cancelled, so we are left with 1 minus log a divided by a square, right? So now let us simplify it further. So we can now write 0 to infinity. Here we have log x dx divided by a square plus x square whole square, and we can take this minus 2a to this side, so we have minus pi over 4a, and here 1 can be replaced by log of e minus, and here we have log of a divided by a square, right? Okay, so now taking this negative sign inside the bracket, so we have pi over 4a cube this is a square, this is a, so a cube, and here we have log of a minus log of e, right? And now we can write it as pi over 4a cube, and by using the properties of logarithms we can write log a over e, right? And this integral was I1, right? So here we have I1. So the value of I1 is given by pi over 4a cube log of a over e, right? So viewers, in this lecture we are deriving some important results, right? So the value of this integral was pi log a over 2a, and the value of this integral is pi over 4a cube log a over e, right? Okay, now here we can make some important deductions here. See, if we take a is equal to 1 here, then see what will we get. If we take a is equal to 1 here, then the integral reduces to 0 to infinity, and we have log x over 1 square is 1, so we have 1 plus x square whole square, and here we have dx, and we take a is equal to 1 here, then we get pi over 4, and log of here will take 1, so we have 1 over e, right? And 1 cube is 1 because we are taking a is equal to 1, right? So this log of 1 over e can be written as we can write minus pi by 4 log of e, right, by using the properties of log, and log e is 1, so we have minus pi by 4 times 1, because log of e is equal to 1, right? So now we can write this expression as minus pi by 4, right? So the value of this integral is equal to minus pi by 4, right? So similarly, we can derive other results by assigning different values to a, right? So this is how we can analyze these integrals.